Hello my precious friends and welcome to our today's class. It is our first lesson on the 8th topic of Form 3 work, which is called Heating Effect of Electric Current. As usual, let me commence by giving you the quote of the day, which states that your destiny is shaped by the small decisions you make each day. We shall discuss that quote at the end of our class today. So today we are looking at the heating effect of an electric current, whereby we'll simply be looking at situations whereby an electric current can bring about what we call a heating effect. So let's start by looking at case scenarios whereby a current produces a heating effect. So our first case scenario is in an electric bulb, whereby it is observed that whenever an electric bulb is connected in an electrical circuit with the supply of current, it is observed that that particular bulb feels somehow hot. That is when the switch is closed, or when the current is flowing through that particular electrical circuit. So what happens is that we have what we call the electrical energy that is flowing. So that particular energy is lost due to some materials within that particular bulb that resists the flow of that particular current, so that instead of all the electrical current being converted into light energy, some of the electrical energy is converted into heat energy. That is why the bulb feels somehow warmer. So because some of the electrical energy, instead of being converted into light energy, it is converted into the heat energy. So that is what causes the bulb to feel somehow warmer. The second case scenario whereby a current produces a heating effect is in an electric coil, whereby an electric coil is usually made of a material of very high electrical resistance, such that when electrical energy or when current flows through that particular coiled resistor wire, most of the electrical energy is actually lost in form of heat, or simply the electrical energy is converted into heat energy. So that heat energy is what brings about what we call a heating effect. So those are two case scenarios that show that an electrical current flowing within a circuit can bring about what we call a heating effect, or it can produce heat. Next, let's look at the factors. That is the factors affecting the heating effect of an electric current. So the first factor is the resistance of the conductor. So whereby, of course, if a material that is used within a given circuit, or if the material of the conductor is made of a material of very high electrical resistance, then we expect most of the electrical energy to be lost in form of heat, or we expect most of the electrical energy to be converted into heat. Therefore, the heat developed H is directly proportional to the resistance R of the material used. So this simply means that the higher the resistance of the material used, the more the heat will be produced, or the more the electrical energy that will be resisted, and causing the electrical energy to be converted into heat energy. And of course, the lower the resistance of the conductor, the lower the resistance of the electrical current, hence less electrical energy will be converted into heat energy. So the heat energy developed is simply directly proportional to the resistance of the conductor used, or of the material of the conductor used. The second factor affecting the heating effect of an electric current, or the second factor that affects the amount of heat, that is the amount of electrical energy that will be converted into heat energy, is the time for passing the current through a conductor. The time for passing the current through a conductor. So obviously, if the current passes through a conductor for a longer time, that increases the chances of that particular current being resisted. Therefore, the longer the time of passing the current within a conductor, the higher the resistance of that particular current. And of course, when current is resisted, that simply means that the electrical energy will be converted into heat energy. Therefore, the longer the time t of passing the current through a conductor, the greater the heat energy developed. Therefore, the heat energy developed is directly proportional to the time of passing the current through a conductor. So that simply means if you pass current through a conductor for a longer time, we expect that current to be resisted. Hence, most of the electrical energy will be converted into heat energy. Therefore, the longer the time of passing electrical current through a given conductor, the higher the heat developed, or the higher the electrical energy that will be converted into heat energy. Then the third factor is the amount of current passing through a conductor. So obviously, when more current is passing through a conductor, we expect most of it to be resisted. But when just a small amount of current is passing through a conductor, we expect less current to be resisted. Therefore, for a given resistance and time, heat produced is directly proportional to the square of the current that is flowing through that particular conductor. Therefore, the heat developed or the heat lost, that is the electrical energy which is lost in form of heat, is directly proportional to the square of the current passing through that particular conductor. So the higher the amount of current, the more the resistance, therefore the more the electrical energy that will be converted into heat energy, hence more heat energy will be produced. Now, if I combine equation 1, equation 2, and equation 3, we shall have the following. So from equation 1, we can see that H is directly proportional to R. From equation 2, H is directly proportional to T. Then from equation 3, H is directly proportional to the square of current. So if I combine all these three equations, you can see from equation 1 we have H, equation 2 we have H, and equation 3 we have H. So I'll just take one value of H. Then of course H from equation 3 is directly proportional to the square of current. Therefore H is directly proportional to I squared. From equation 1, H is directly proportional to the resistance R. Therefore I just put my R here because it is also directly proportional. Then H, that is from equation 2, H is directly proportional to the time of passing the current. Therefore H will also be directly proportional to T. So combining the three equations, we shall have H being directly proportional to the square of current multiplied by resistance, also directly proportional to the time of passing the current through a conductor. Therefore, from mathematics, we know that to remove the proportionality symbol, we have to introduce equal signs with a constant. So I'll let my constant be K. Therefore, H will be equal to, so equal sign and constant, they are simply representing my proportionality symbol. So H will be equal to K, current squared, multiplied by resistance times the time. Then if I let K to be equal to 1, this equation will disintegrate into, if K is 1, so this one will simply become H is equals to 1 times I squared RT, which is just the same as saying H is equals to I squared RT. Therefore, this is the formula that we use to find the amount of heat developed, that is within a given circuit due to the flow of an electric current. So H, or the work done, will be equal to I squared RT, where I squared is the amount of current flowing through a conductor, R is the resistance of the conductor, and T is the time for passing the current within that particular conductor. So next, let's look at the work done by an electric current. So we say that an electric current I does work when it passes through a conductor. So the work done becomes transferred to internal molecular energy in the conductor, accompanied by a rise in temperature. So this energy may be given out in form of heat. Remember, for current to flow, we defined current from cells and simple circuits. We did say that that is the last topic of Form 1 work. You can just refer on this channel, that is cells and simple circuits. It was our last topic on Form 1 work. We did say that current simply refers to the rate of flow of charges. So when we talk of an electric current does work when it passes through a conductor, we simply means that there is work that is being done to move an electron from one point of a conductor to another point of that particular conductor. So the work done in moving an electric charge or an electron from one point of a conductor to another, that is what we are calling the work done by an electric current. And of course, that work, when it is being done, we shall experience a rise in temperature of the conductor, because some of the work will be lost in form of heat. So some of the electrical energy will actually be converted into heat. That's why we are going to experience a rise in temperature. So this energy may be given out in form of heat, because it is just electrical energy being lost in form of heat. Therefore, the work done, that is from current electricity 2, the first lesson, we did say that work done by an electric current or by an electric charge is equals to the product of charge and the potential difference. So the work done, which is W, will be equal to the charge, which is simply Q, multiplied by the potential difference, which is actually V. But from cells and simple circuits, that is the last topic under Form 1 work that we have covered in this particular channel, you can just refer. We did say that the charge Q is equals to the product of current and the time for passing the current through that particular conductor. Therefore, if I substitute IT for Q in this particular equation, this equation will become work done W is equals to, where I have Q, I want to substitute with IT, so this will be ITV. So Q will be equal to ITV. Then of course, I can rewrite this as work done is equals to VIT. So this is another formula that we use to find the work done by an electric charge or an electric current for the charge to move, or for an electron to move from one point of a conductor to another. Then we can also express this particular formula in a different format, that is from Ohm's law, which we covered under current electricity 2, that is a form 3 topic, which again we have covered in this chapter. We did say that the voltage V is equal to the product of current and the resistance R. So I want to substitute IR for V in this particular equation. So where I have V, I want to substitute with IR, which is the equation of the Ohm's law. Therefore, this equation will become, work done will become, where I have V, I'm substituting with IR. So this equation will become IR multiplied by I times T. So IR multiplied by I times T. Then of course, current times current, or I times I simply get I squared. Then I still have R and T. So the work done can also be given by I squared RT. Then we can also express this one in terms of V, R, and the time alone. That is, we just want to substitute the value of current. Then again, from Ohm's law, if we make I subject of the formula for the Ohm's law equation, which was V is equals to IR, so the current I will be equal to V over R. So I want to substitute V over R for I in this particular equation. So where I have I want to substitute with V over R. So this equation will become work done is equals to the current I is V over R. So that simply means that I squared will be equal to V squared over R squared. So if I substitute I squared, I'll simply get work done being equal to V squared over R squared. Remember, V squared over R squared is simply the I squared, because I squared from here is just V squared over R squared. So this equation will become V squared over R squared, which is the I squared. So V squared over R squared multiplied by RT. So multiplied by RT. And then of course we have one R up here, then we have R squared down here. So if I divide, so one R will cancel with one R on the denominator, so that we remain with just V squared over RT. So the work done by an electrical charge or by an electric current to flow from one point to another is equals to the heat energy developed, which is simply equal to V squared over R multiplied by T. So these are the three formulas that we use to find the work done by an electric charge. So the first formula is work done can be given by VIT. Second formula, work done can be given by I squared RT. Then the third formula is that H is equals to V squared over RT. So don't try to cram these formulas. Instead, just know one of the formulas, then be in a position to use the Ohm's law equation and the Q is equals to IT equation to substitute and get the other formula. So just know one formula, then be in a position to derive the other formulas. So I'm giving you different formats of the same equation because you will be encountering questions demanding the use of one of these equations, that is to calculate the work done by an electric current. Next, let's look at examples on how we can apply the formulas that we have just derived from a previous slide. So example 1 reads that the potential difference across a lamp is 12 volts. How many joules of electrical energy are changed to heat and light when, part A, a charge of 5 coulomb passes through it? So just highlight the values that we are given. So one, we are given the potential difference V. We are also given the that is the charge, which is in coulomb, which is actually 5 coulomb. So they want us to find the electrical energy. So we have just said that electrical energy can be given by charge Q multiplied by the potential difference V. So the formulas that you use will depend on the values that are provided on the question and the demands of that particular question. Like in this case, you are given the potential difference V, we are also given the charge Q. Therefore, the most appropriate formula for the work done or for the electrical energy will simply be given by Q, that is the charge Q multiplied by the potential difference V. So of course, the charge Q, part A, we are given as 5 coulomb. So this will be 5 coulomb multiplied by the potential difference, which is actually 12 volts. So 5 by 12, you simply get the electrical energy of 60 joules. Then part B, we are given a current of 2 amperes. So now we have a current of 2 amperes. Then that flows through the lamp for 10 seconds. Of course, this is time. So we are given the current, we are given the time, we also have the potential difference V. So we look for the formula of electrical energy, whereby the formula that utilizes the potential difference V, the current I, and also the time T, that is in seconds. And of course, we have just derived and said that the formula for the work done or the electrical energy can be given by VIT. That is the product of the potential difference, the current flowing through the circuit, and the time taken for that particular current to flow within that circuit. So work done will be equal to VIT. Of course, potential difference V, we are given as 12 volts, multiplied by the current in amperes is 2 amperes. That is for part B. Then the time is 10 seconds. So 12 times 10 times 10, that is 12 times 2 times 10. You will simply obtain the work done or the electrical energy of 240 joules. Then in our second example, it reads that an iron box has a resistance coil of 30 ohm. So of course, this is the resistance R, and takes a current of 10 amperes. So this is the current I. Calculate the heat in kilojoules developed in 1 minute. So of course, we are given time as 1 minute. Then we know that 1 minute is equivalent to 60 seconds. So I'm converting to seconds because we know that the SI unit for time is actually seconds. That is from 1, that is what we said. So from this question, we are given the resistance R. So we have the resistance R, we have the current, which is 10 amperes. You also have the time, which is 1 minute, which is equivalent to 60 seconds. So they want us to calculate the heat in kilojoules developed. So the heat developed is simply equal to the work done to move that particular charge. So we'll simply say that we'll use the formula that involves R, I, and T. So the formula that you apply will depend on the values that you are provided on the question and the demands of that particular question. Therefore, the heat in kilojoules developed will simply be, we'll use the formula for heat is equals to I squared RT, which we have just derived from our previous slide. So the current we are given as 10 amperes, so that will be I squared, so we'll have 10 squared, times the resistance we are given as 30 ohm, which is 30, multiplied by the time is actually 1 minute, which is equivalent to 60 seconds. So that we have 10 squared, we'll simply get 100. So 100 times 30 times 60, so that will give you 180,000 joules. So, but the question wants us to calculate the heat in kilojoules. They want the heat in kilojoules. Again, we have also said that 1,000, that is from our previous slide, we did say that from a previous slide, we did say that 1,000 joules will always be equal to 1 kilojoule. So whenever we have a kilojoule, that is K, then 1,000. It is always associated with 1,000. So 1,000 joules is equals to 1 kilojoule. What about 180,000 joules? So that will be 180,000 joules divided by 1,000 joules multiplied by 1 kilojoule. Of course, the 3 zeros will cancel with the 3 zeros, so that will remain with 180 kilojoules as the heat in kilojoules developed in 1 minute. Then lastly, I have an exercise here that I do recommend you should try at your own free time to gauge your understanding of the examples and the concepts that you have learned in this particular lesson. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that your destiny is shaped by the small decisions you make each day. So the quote is reminding us about the impact of our daily decisions on our long-term destiny or on our long-term future. The quote is also encouraging us to always make the right decisions each day, because a combination of good decisions or right decisions will always result into a happy life and a fulfilling life. And lastly, recall that your current lifestyle is a product of your decisions and not a product of your circumstances. So thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you're new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. I know it's been long since I uploaded a video, but I just want to thank you for your patience. Thank you for your continued support. Thank you for your encouraging comments. I really appreciate. Until next time, this is Kind Tuition Academy.